All right, today we're going to be discussing polynomial functions, and these are the content standards and mathematical practice 4 that we're going to use on our assignment. Previously, you've analyzed graphs of quadratic functions, and today we're going to evaluate polynomial functions and identify general shapes of graphs of polynomial functions. Our new vocabulary is polynomial in one variable, leading coefficient, polynomial function, power function, quartic function, quintic function, and end behavior. All right, now a polynomial in one variable is simply an expression in this form where a to 0 are real numbers and n is a non-negative integer. Polynomial that's written in standard form when the values of the exponents are in descending order. So you'd have x to the fourth, x to the third, x squared, x1. The degree of the polynomial is the value of the greatest exponent. The coefficient of the first term of a polynomial in standard form is called the leading coefficient. So the constant has no variable with it. It has a degree of 0, so its leading coefficient would be 12. A linear equation, which means x to the first power, has a degree of 1, and notice that the coefficient that is with it is 4. A quadratic is to the power of 2, so it's a degree of 2, and the leading coefficient is the constant that's with it, the base that's with it. A cubic function is to the power of 3, so it's a degree of 3, and in this case the leading coefficient is 8. And then in general, a to the n degree, because that's the exponent, and the leading coefficient is a to the n. We're to state the degree and leading coefficient of this polynomial, and if it's not a polynomial in one variable, we are to explain why. So this is a polynomial in one variable. Notice that we only have a z here. So the degree is 3, that's the exponent of the largest variable, and the leading coefficient is 7. Another example. Is this one a polynomial in one variable? What do you notice? We notice that it has an a and a b, so this one's not a polynomial in one variable. What about this one? First of all, is it written in descending order? That's the first thing I would do. Write it in standard form in descending order. It makes it easier for you to spot your leading coefficient and your degree. It is in one variable. The largest degree is 6, so the leading coefficient is a -8. The sign stays with it. Okay, it's time for you to check your progress. So pause the video for a moment, answer the question, and then come back and check your answer. Did you get that it's a degree of 3 with a leading coefficient of 3? Excellent. That is our leading variable. Let's try another one. So pause the video for a moment and then come back and check your answer. Oh, this one is a little tricky. It had 2 variables, so it's not a polynomial in one variable. One more. So pause and then come back and check your answer. This one is a polynomial in one variable, but it is not written in standard form. The degree is 7, and so the leading coefficient is a -5. Now, a polynomial function is a continuous function that can be described by a polynomial equation in one variable. For example, 3x cubed minus 4x plus 6 is a cubic polynomial function to the degree of 3. The simplest polynomial function of the form f of x is equal to ax to the b, where a and b are real numbers, are called power functions. So if you know an element in the domain of any polynomial function, you can find the corresponding value in the range. For example, we're looking at a real-world example where we're to evaluate a polynomial function. So I want you to pause the video for a moment and read through the problem, and then we'll go on to continue our work. All right, we're asked to find the volume of air in the lungs 1.5 seconds into the respiratory cycle. So all we're simply going to do is substitute 1.5 into the function. So the function is for t, so everywhere you see a t, we're going to put 1.5. As you notice, that's what we've done here. Put 1.5 everywhere you see the variable. Now we're going to simplify. 1.5 to the third power times its coefficient. and then we simply add them. So it's approximately equal to 0.4766 liters. So we were just evaluating. So let's check your progress. I'll give you a moment to do that. Pause the video, work this problem, then come back and check your answer. Did you get close to 11.6? I ended up with 11.5625 by the time I finished the math. I simply substituted 1.25 in each time for t. You can also evaluate functions for variables and algebraic expressions. So this gets a little trickier. What you need to do is make sure that you're lining up everything appropriately as you're working. You can get lost so very easily. So we're to find b of 2x minus 1 minus 3b of x if b of m is 2m squared plus m minus 1. So let's look at this one. 2m squared plus m minus 1, that's our original function. Now let's find out what would happen here. Evaluate this one for 2x minus 1. So we're going to simply replace 2x minus 1 every time we see an m. Combine our like terms. Now we're going to evaluate 3bx, so 3 times b of x. We're going to go back to this original function, and everywhere we see an m, first of all, we've got to multiply it by 3, and then we're going to put an x everywhere we see an m. Use the distributive property. Make sure you multiply that 3 by every term inside the parentheses. Now we've got two different answers. We've evaluated the original function for 2x minus 1, and we have evaluated the function for 3b of x. So we're going to take our answer that we got for our first evaluation, and we're going to subtract from it, notice we're subtracting, what we got when we evaluated the second part. We're going to distribute that negative 1 across the parentheses behind it, combine any like terms, and so here's our answer. We end up with 2x squared minus 9x plus 3. So that's where it's very important that you follow along and understand which answer is going with which one, because you have to go back and plug them in again. All right, time for you to check your progress. So pause the video for a moment, work the problem, then come back and check your answer. All right, I got 2x squared plus 4x minus 2. When I evaluated the original function for 2x plus 1, I ended up with 4x squared plus 4x plus 4. Then when I evaluated this same function for 2g of x, I ended up with 2x squared plus 6. When I subtracted 2x squared plus 6 from the 4x squared plus 4x plus 4, I simplified and ended up with this answer. So if you didn't get that, why don't you go back and try it again. Graphs of polynomial functions. These are the general shapes of the graphs of several polynomial functions. They show the maximum number of times the graph of each function may intersect the x-axis. So notice this one, degree of 0 doesn't ever. Degree of 1 intersects 1 time. Degree of 2, 2 times. Oh, what are you noticing here? So this is the same number as the degree of the polynomial, is it not? If it's a degree of 3, it can cross the x up to 3 times. Degree of 4, up to 4. Degree of 5, up to 5. The domain of any polynomial function is all real numbers, and the end behavior is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and leading coefficient of a polynomial function determine the end behavior of the graph and the range of the function. So notice on this one, even functions, the ends are both going the same direction on even functions. If it's positive, they point up. If it's negative, it points down. If your degree of your function is odd, however, notice the ends, this one's going this way and this one's going that way, so that you can tell an odd or an even function by the end behavior. As x approaches positive infinity, the function also goes towards positive infinity. As x approaches negative infinity, the function also approaches positive infinity. Look at that. So both times the function is going toward positive infinity. Doesn't matter if x is going positive or negative. Let's look at this one. As x approaches positive infinity, the function approaches negative infinity. As x approaches negative infinity, the function approaches negative infinity as well. Let's look at the odd. As x approaches positive infinity, the function approaches positive infinity. As x approaches negative infinity, the function approaches negative infinity. And finally, an odd negative, as x approaches positive infinity, the function approaches negative infinity. As x approaches negative infinity, the function approaches positive infinity. So this is a key concept about odd and even degree functions. The number of real zeros of a polynomial function can be determined by examining its graph. Recall that real zeros occur at x-intercepts, so the number of times a graph crosses the x-axis equals the number of times of real zeros. So we're going to look at the graph, and there's several things we're going to do. We're going to describe the end behavior, we're going to determine whether it's odd or an even function, and we're going to state the number of real zeros. So looking at this one, we got a frowny face going on here. Must be Monday. Okay. So this graph, as x approaches positive infinity, this graph, this function approaches negative infinity. As x approaches negative infinity, the function approaches negative infinity. It is an even degree polynomial because the ends are going the same direction. And this graph does not intersect the x-axis, so it has no real zeros. Let's look at another one. So stop and ask yourself, as x is going towards positive infinity, what's happening to the end behavior of the graph? It's going toward positive infinity as well. Now, what's happening as x approaches negative infinity? What's happening to the end behavior? It's also approaching negative infinity. Notice the notation, how you write this. This little arrow means approaches, as x approaches positive infinity. It is an odd degree polynomial because the ends are going in separate directions. And the graph intersects the x-axis at exactly 1 point, so the function has one real zero. All right, time for you to check your progress. So looking at this graph, I want you to stop and evaluate it and see which one of these is the correct answer. So it's an even degree, the ends are going the same direction, and it has two real zeros. Excellent job. One more. So pause the video, answer this question, and then come back and check your answer. Well, this one's very easy to see that it's an odd function because the ends are going in separate directions, and it has 1, 2, 3 real zeros. Excellent job, everybody. You're ready to start working the assignment.